The Jetson One may be one of the most important personal aircraft of the modern era. Not because it flies the farthest, not because it carries the most weight, and certainly not because it is the cheapest aircraft ever built. Its real achievement is much simpler. It made personal electric flight look possible. The aircraft is compact enough to fit inside a garage. It can take off vertically from a small open area. It does not need a runway. And because 8 electric motors are constantly adjusting their thrust, the aircraft can maneuver through spaces that would make a conventional airplane completely useless. It can hover, turn almost inside its own footprint, and fly around obstacles with the kind of control normally associated with a camera drone. That is why so many companies have copied its basic layout. Once people saw the Jetson One flying between trees, over fields and above small private airstrips, the idea no longer looked like science fiction. But the Jetson One also carries a limitation that almost every viewer notices immediately: flight time. Depending on conditions, payload and operating reserve, a compact multicopter like this only remains airborne for a relatively short period. That may be enough for recreational flying. It may be enough to circle a field, climb above the trees, and enjoy a few unforgettable minutes in the air. But the moment you imagine using the aircraft for anything more ambitious, the limitation becomes impossible to ignore. 20 minutes in the sky does not mean 20 minutes away from home. You still need enough energy to return. You need a safety reserve, and wind, temperature, and pilot weight can reduce the time even further. So today, we are going to ask a dangerous engineering question. What if we redesigned the Jetson One? Not by adding a bigger battery, not by making the aircraft much larger, but by changing the entire way it creates lift. Could a Jetson-sized aircraft fly significantly longer using one large rotor, small wings, and dedicated forward propellers? The answer may be yes, but the price of that extra endurance may be much greater than it first appears. Before changing the Jetson One, we need to understand why its original design is so effective. At first glance, the aircraft looks simple: a lightweight frame, a central pilot seat, and 8 electric motors arranged in 4 coaxial pairs. But that arrangement gives the aircraft several major advantages. First, there is no large mechanical transmission connecting one engine to a complicated rotor system. Each electric motor can be controlled independently. If the flight computer needs the aircraft to roll right, it can increase thrust on one side and reduce it on the other. If it needs to pitch forward, it changes thrust between the front and rear motors. Yaw control is produced by carefully balancing the torque of propellers rotating in opposite directions. There is no traditional helicopter tail rotor, no large gearbox, no long mechanical drive shaft, and no pilot manually coordinating collective pitch, cyclic control, and anti-torque pedals. The computer does most of the work. This is one reason multicopters feel so stable. The pilot gives a command. The flight control system translates that command into hundreds of tiny motor adjustments every second. Multiple motors also provide a degree of redundancy. If one motor loses power, the remaining motors may be able to compensate long enough to keep the aircraft under control. That is extremely difficult to achieve with a single lifting rotor. The original Jetson layout is therefore not an accident. It is compact, mechanically simple, electronically controllable, and highly maneuverable. But every engineering advantage comes with a cost, and the cost of using many small rotors is efficiency. To understand the endurance problem, we need to talk about something called disk loading. It sounds technical, but the idea is simple. Every rotor sweeps through an invisible circular area. That circle is called the rotor disk. To keep an aircraft in the air, the rotor must push air downward. The larger the disk area, the more air the rotor can move. And if the rotor can move a larger amount of air more gently, it usually requires less power than moving a smaller amount of air much faster. Imagine trying to support your weight on deep snow. If you wear normal shoes, your weight is concentrated over a small area and you sink. If you wear snowshoes, the same weight is distributed over a much larger area. Rotor disc loading works in a similar way. A helicopter with a large main rotor spreads its weight over a huge circular area. A compact multicopter spreads the same weight across several much smaller discs. That is excellent for packaging, but not ideal for hover efficiency. For a simplified comparison, imagine the Jetson-style aircraft has 4 effective rotor positions, each roughly 1 meter in diameter. Together, those 4 rotor discs provide an area of approximately 3.14 square meters. Now replace them with one rotor measuring 2.7 meters across. The total swept area becomes approximately 5.72 square meters. That is around 82% more rotor disc area without dramatically increasing the overall geometric footprint of the aircraft. And that difference changes everything. Here is the proposed design. Instead of 8 small motors and 4 coaxial rotor positions, the aircraft uses one large main rotor with a diameter of around 2.7 meters. The pilot remains seated beneath the center of the rotor. The frame stays narrow and lightweight. But 2 short wings extend from either side of the aircraft. Mounted near the tips of those wings are small horizontal propellers. These propellers have 2 jobs. During forward flight, they push the aircraft through the air. During hover, they assist with yaw control and help counteract the torque created by the main rotor. At the rear, 2 canted stabilizers provide directional stability as the aircraft gains speed. The result no longer looks like a pure multicopter. It becomes something much closer to a tiny electric compound helicopter. A compound helicopter combines a main rotor with wings or separate propellers. The main rotor handles vertical lift. The side propellers provide forward thrust. And the wings gradually take over some of the lifting work as speed increases. This matters because the original Jetson One must tilt its entire body to move forward. Its lifting propellers then produce both vertical and horizontal force at the same time. In the redesigned version, the main rotor can remain focused primarily on lift, while the smaller propellers handle propulsion. At least in theory, each part of the aircraft is now doing the job it performs most efficiently. But theory is only useful if the numbers support it. Let us assume the aircraft, including the pilot, has a total mass of approximately 200 kilograms. That gives us a weight force of roughly 1,960 newtons. With an effective rotor area of around 3.14 square meters, the Jetson-style multicopter has a disc loading of approximately 64 kilograms per square meter. For the redesigned single-rotor aircraft, the disc loading drops to around 35 kilograms per square meter. That is a very large reduction. Using basic momentum theory, the ideal power required to hover the multicopter configuration comes out to approximately 31 kilowatts. The single large rotor requires closer to 23 kilowatts. That is a reduction of more than 25% before considering several other losses. And in electric aviation, 25% is enormous. Battery aircraft live and die by small improvements. Saving 1 kilowatt matters. Saving 8 kilowatts could add several minutes to every flight. But ideal momentum theory assumes perfect rotors operating in perfect conditions. Real aircraft are not perfect. Blades create drag. Motors lose energy as heat. Controllers are not 100% efficient. The airframe interferes with the airflow. And the coaxial layout of the Jetson-style aircraft adds another penalty. The Jetson One uses coaxial rotor pairs. That means one propeller is positioned above another on the same lifting arm. This is a clever way to fit more thrust into a compact footprint. But the lower propeller does not operate in clean, undisturbed air. It sits inside the accelerated airflow created by the upper propeller. The two rotors therefore interfere with each other. They still produce useful thrust, but they do not perform as efficiently as two completely separate rotor discs operating in fresh air. The exact penalty depends on rotor spacing, blade geometry, operating speed, and many other details. For a simplified concept estimate, we could apply an overall efficiency factor of around 80%. That would raise the real hover power requirement of the multicopter from the ideal 31 kilowatts to somewhere closer to 39 kilowatts. Now assume the aircraft carries a battery with approximately 13 kilowatt-hours of total capacity. The pilot cannot safely use every last unit of energy. The aircraft needs a reserve. The battery management system also protects the cells from complete discharge. If around 80% of the pack is practically usable, the aircraft has just over 10 kilowatt-hours available. Divide that usable energy by a power draw near 39 kilowatts, and the endurance lands in the general region of 15 to 16 minutes of continuous hover. That is surprisingly close to the short-duration flights associated with this class of aircraft. The model is simplified, but it shows that the endurance problem is not mysterious. The aircraft is using a large amount of power to push a relatively small amount of air downward. So what happens when we repeat the calculation with the large rotor? Using the same simplified battery assumptions, the ideal answer looks impressive. If the large rotor only requires around 23 kilowatts in hover, the theoretical endurance approaches 26 minutes. That is roughly 70% longer than the 15-minute estimate for the coaxial configuration. At first glance, it looks like the redesign has solved the problem. But this is where an honest engineering analysis must slow down. The 23 kilowatt number is ideal rotor power. It does not include all real-world losses. The aircraft would need power to overcome the drag of the rotor blades. The motor and inverter would generate heat. The main rotor would need a strong mast, bearings, and a control system. The side propellers may need to run during hover to counter rotor torque. The wings and tail would sit inside disturbed airflow, and the larger rotor system could add weight. Once those penalties are included, the real hover requirement might rise into the high 20s or low 30s of kilowatts. That would reduce endurance. Instead of a guaranteed 26 minutes, a more realistic target might be somewhere in the low 20s, depending on how efficiently the aircraft is engineered. That is still a meaningful improvement, but it is not free energy. And hover is only half of the story. The true advantage of the redesign may appear once the aircraft begins moving forward. A multicopter is most comfortable in hover. Its rotors create lift directly. But when the aircraft moves forward, it must tilt. Part of the rotor thrust continues supporting the aircraft. The remaining part pushes it ahead. The faster it tries to fly, the more complicated the force balance becomes. A wing solves that problem differently. Once air flows over a wing, the wing can generate lift without using a motor to push air directly downward at every moment. The motor still uses power to overcome drag and maintain speed, but the wing can produce lift much more efficiently than a hovering rotor during forward flight. That is why airplanes can travel much farther than helicopters using the same amount of energy. In our redesigned aircraft, the short wings would do very little during hover. But as the side propellers accelerate the aircraft, the wings would begin producing lift. At a suitable cruise speed, they might carry a substantial share of the aircraft's weight. Perhaps 30%? Possibly 40 or even 50% in an optimized design. That would allow the main rotor to reduce its lifting load. The rotor would not stop producing lift, but it would no longer carry the entire aircraft alone. This is the basic principle behind compound helicopters. A rotor provides vertical takeoff and low-speed control. A wing supports the aircraft during cruise, and a separate propeller creates forward thrust. The system is more complicated than a multicopter, but it can be much more efficient once the aircraft begins traveling. For a personal aircraft, that could mean the difference between a 15-minute joyride and a useful short-range journey. There is one major issue with using a single main rotor: torque. When the motor spins the rotor in one direction, the rotor pushes the aircraft body in the opposite direction. A conventional helicopter solves this with a tail rotor. The tail rotor produces sideways thrust that prevents the fuselage from spinning. Our redesigned aircraft does not have a conventional tail rotor. Instead, it uses the two propellers mounted on the short wings. By changing the thrust produced by the left and right propellers, the flight control system could create a yawing moment around the aircraft's center. But this is more difficult than it first sounds. If both propellers only push forward, changing their thrust will produce yaw control, but it may also create unwanted forward movement. A practical version may therefore require variable pitch propellers, reversible thrust, or a more sophisticated vectoring system. During cruise, both propellers could produce forward thrust. During hover, one propeller might increase thrust and the other decreases, reverses, or changes blade pitch to create the required anti-torque moment. This is possible. Electric motors respond quickly. Modern flight computers can coordinate complex control systems. But it adds another layer of engineering that the original Jetson ONE does not need. The multicopter cancels torque by using rotors spinning in opposite directions. The single-rotor aircraft must actively fight torque every second the main rotor is powered. That requires energy. It requires control authority. And it requires a safe response if one side propeller fails. The original multicopter gains safety from redundancy. It has multiple motors, multiple propellers, and multiple electronic speed controllers. A failure in one component does not automatically remove all lifting power. A single-rotor aircraft appears more vulnerable. If the main motor stops, the aircraft loses its primary source of powered lift. But helicopters have used a different emergency system for decades: auto-rotation. When a helicopter loses engine power, a freewheeling unit disconnects the engine from the rotor. As the aircraft descends, air moves upward through the rotor disc. That airflow keeps the blades spinning. The pilot stores energy in the rotor and uses it during the final flare to reduce the descent rate before touchdown. In theory, the redesigned aircraft could use the same principle. A one-way clutch would allow the main rotor to continue spinning after the electric motor stopped. A large rotor would also carry more rotational inertia than small multicopter propellers. That stored energy could help during an emergency landing. But auto-rotation is not a magic parachute. It requires the correct rotor design. The blades may need collective pitch control. The system needs sufficient rotor inertia. And most importantly, the aircraft needs enough altitude or forward speed to establish auto-rotation. A power failure only a few meters above the ground may leave almost no time to react. This is especially important because Jetson-style aircraft are often shown flying low, near trees and over open fields. So auto-rotation could improve safety, but it would not completely replace the redundancy of 8 independent motors. The two systems protect against failure in very different ways. The original Jetson-style multicopter controls movement by changing motor speed. That is one of its greatest strengths. The propellers are relatively simple. The flight computer commands more or less power, and the aircraft responds. A large helicopter rotor is more complicated. Changing the rotor speed is usually too slow for precise control. Instead, helicopters control lift by changing the pitch angle of the rotor blades. Collective pitch changes all blades together and increases or decreases total lift. Cyclic pitch changes blade angle at different points during rotation, tilting the rotor disc and moving the aircraft sideways or forward. That normally requires a swash plate, pitch links, bearings, and a carefully engineered rotor head. These components add weight. They require maintenance. They experience vibration and fatigue, and they create failure modes that do not exist in a fixed-pitch multicopter. The redesign could possibly use an unconventional rotor control method, a tilting mast, individual blade control, or a simplified rigid rotor. But none of those options are trivial. This is the central trade-off of the entire concept. The large rotor improves aerodynamic efficiency, but it reduces mechanical simplicity. The original Jetson One uses more motors and more propellers. The redesigned version uses fewer lifting motors but requires a far more sophisticated rotor system. One aircraft solves complexity with electronics. The other solves it with rotorcraft engineering. On paper, the 2.7-meter rotor fits inside roughly the same overall space as the Jetson-style multicopter. But footprint is not the same thing as operational clearance. The original aircraft has multiple small propellers surrounded by a relatively compact frame. Its thrust can change rapidly. The flight controller can produce aggressive roll, pitch, and yaw corrections almost instantly. A large rotor behaves differently. It carries more inertia. Its blades sweep through a wide, circular area. The rotor tips move quickly and create a much larger hazard zone. Flying near a tree trunk may become far more dangerous. A branch that misses the aircraft's body could still strike the main rotor. And because the rotor is mechanically connected through one central system, damage to a single blade could affect the entire aircraft. The larger rotor may also respond more slowly to sudden control commands. That does not mean the aircraft would be difficult to fly. Modern rotorcraft can be extremely agile, but it would probably not feel exactly like the original Jetson One. The original design is almost like a giant drone. The redesign would feel more like a tiny helicopter. So even if the dimensions remain similar, the mission changes. The multicopter is optimized for compactness, control, and simplicity. The compound helicopter is optimized for endurance and forward flight efficiency. You may not be able to maximize both. The entire endurance calculation assumes the redesigned aircraft weighs approximately the same as the original. That may be possible, but it cannot be assumed. Removing 8 lifting motors and 8 speed controllers could save a significant amount of mass. Small electric motors may each appear light, but the total includes wiring, mounts, propellers, controllers, and structural reinforcement. The redesign replaces those parts with one larger motor, but it also adds a main rotor hub, a strong rotor mast, large blades, blade pitch controls, a freewheeling clutch, 2 wings, 2 cruise propellers, 2 additional motors and controllers, a tail structure, and stronger attachment points to handle rotor loads. A single large rotor also produces major bending and vibration forces through the center of the aircraft. The frame may need to become stronger, and stronger usually means heavier. If the redesign gains only 10 or 20 kilograms, its disc loading rises. The hover power increases. The wings need to produce more lift, and some of the theoretical endurance advantage disappears. This does not make the concept impossible. It simply means the next step cannot be another equation. It must be a detailed mass budget. Every motor, every blade, every bearing, every meter of wire. Until the complete aircraft is weighed, the 26-minute figure remains a target, not a result. If the engineering challenges can be solved, the redesigned aircraft could offer several important advantages. First, the larger rotor disc reduces disc loading. That lowers the ideal power required for hover. Second, The aircraft avoids much of the interference created by coaxial rotor pairs. Third, the side propellers generate forward thrust without forcing the entire aircraft to tilt aggressively. Fourth, the wings begin creating lift during cruise. This unloads the main rotor and may improve range. Fifth, a properly designed main rotor could potentially auto-rotate after a complete power failure. And finally, the system could be optimized for traveling rather than simply hovering. That distinction matters. The original Jetson One is extremely good at staying compact and moving through confined spaces. The redesign would aim to become a more useful point-to-point aircraft. It might not fly twice as long. But even a 30 or 40% increase in practical endurance could dramatically expand the mission. A 15-minute recreational flight becomes 21 minutes. A 20-minute flight becomes 28. That additional time could provide a larger safety reserve, greater range, or the ability to deal with unexpected wind. In electric aviation, extra minutes are not a small improvement. They are the difference between a demonstration and a useful vehicle. But the redesigned aircraft would also lose several qualities that made the Jetson One successful. It would lose mechanical simplicity. A multicopter can use fixed-pitch propellers and direct-drive motors. A large rotor may require pitch control mechanisms and a complex rotor head. It would lose some redundancy. 8 motors create multiple independent sources of lift. One main rotor concentrates the lifting system into a single critical assembly. It may lose some maneuverability near obstacles. A large rotor requires more operational clearance and creates a wider danger zone. It could become more expensive to manufacture. Precision rotor components, bearings and blade controls require tight tolerances. Maintenance may become more demanding. And certification could become more difficult because the aircraft combines the risks of a helicopter, a winged aircraft, and an electric propulsion system. This is why the original Jetson One should not be described as badly designed. It is optimized for a specific mission: short recreational flights, simple control, compact storage, and a flying experience that feels accessible to people who are not traditional helicopter pilots. The redesign does not correct a mistake. It chooses a different compromise. And that is what aircraft design is really about. Not creating a perfect machine, but deciding which limitations matter most. So, could a Jetson-sized aircraft fly longer using one large rotor, short wings, and horizontal propellers? Yes. The physics supports the basic idea. A larger rotor disc can reduce hover power. Wings can provide efficient lift during forward flight. Separate propellers can push the aircraft forward without forcing the main rotor to perform every job at once. And a compound configuration could offer much greater endurance than a pure multicopter. But it would no longer be a simple Jetson One upgrade. It would be an entirely different aircraft. A small electric compound helicopter. More efficient, potentially longer ranged, possibly capable of auto-rotation. But also heavier, mechanically more complex, and dependent on a highly sophisticated control system. The ideal calculation suggests an endurance approaching 26 minutes using the same battery. A real aircraft would probably achieve less once losses, torque control, and additional weight are included. Even so, the improvement could still be substantial. And perhaps that is the real lesson. The Jetson One did not fail to solve personal flight. It proved that compact electric flight could be exciting, controllable, and real. Its short endurance is not evidence of poor engineering. It is the price of choosing simplicity, redundancy, and extreme maneuverability. A large rotor version would choose something else: efficiency, range, and better forward flight performance. So the question is not whether this new design is better. The real question is, better for what? Would you choose the simplicity and agility of the original Jetson One? Or would you accept greater complexity in exchange for more time in the sky? Let us know in the comments. And if you enjoyed this engineering concept, subscribe for more aircraft designs, aviation technology, and ideas that could shape the future of personal flight.